In this video, we're going to learn about the common ways in which we can organize quantitative data versus the previous videos organizing qualitative data. So in the example I gave in the previous video, we looked at the state of birth. There was only a few different possible values, California, Arizona, Nevada, and New York. However, if you look down the example data down here, it's just a bunch of decimal numbers. In fact, I'm pretty sure there's not even a single repeat there. So if you try to do like a bar graph type of situation with this, it wouldn't be very interesting because every single value is different. So they all have a frequency of 1. It's not a very interesting looking graph. So what's very common in quantitative data is to take your data and break it up into classes rather than leaving the data alone. Now, again, there's a lot of decision making going into when we're trying to make classes. How many classes do we want? How big do we want the classes to be, etc., etc. And it's really up to the researcher doing the study to decide how they want to do it. For this one, it looks like my kind of smallest data is about 0.49, and my largest data is about 9.23. So you could think I'm somewhere between 0 and 10 here. And let's say I want to do 5 classes. So let's say I have 5 classes. And so I want that. I'm choosing that as the researcher. I want to break it up into 5 classes. And the max data value I have here is 9.23. And the min data value is 0.49. So then if I want to decide how wide each of my classes would be, is I would just take how wide the whole data set is and divide by the number of classes. And if I pull out my calculator and do this calculation here, 9.23 minus 0.49, that gives me 8.74 divided by 5. And I get 1.748. So that means if I start at the very smallest number and go to the very largest number, every 1.748 each step, I'd have exactly 5 classes splitting up the data. But the thing is, you could do that, but then you have all these really weird numbers when you're breaking things up. So a lot of times what we'll do is we'll take this calculation and then we're just going to go ahead and round it to some convenient value. And in this case, I'm going to round it to 2. Rather than dealing with 1.748, I'm just going to say 2 here. And so what you do is we need to create our classes. And my first class, I need to say, what's my starting number that's going to be fitting into my first class? Well, I could pick the very smallest value, 0.49, but again, then everything's based on this weird decimal number. I'm going to go ahead and round down to say 0. And then this class width is going to tell you how much the next starting one is. So for my second class, I would add the class width of 2 to it, so it's going to start at 2. So that means that the first class is going to be everything from 0 up to 2, but not including 2. The second class is going to go from 2 up to 4, not including 4. The third class is going to go from 4 up to 6, not including 6. The fourth is going to be from 6 to 8, not including 8. And the last one is going to be from 8 to 10, not including 10. And we don't have 10 in our data anyways. And in general, if you ever want to find the class width, you always take, so these are called the lower class limits. And then the other number is going to be the upper class limit. And if you ever want to find the class width, you just take the lower class limit from the next class and subtract it from the lower class limit on the previous class, and that tells you your class width. Now here, I did good practice. I made all my classes equally wide. All the class widths are 2. There are some times where individuals will make their data and they will make the classes different lengths, different widths. You probably don't want to do that. There might be some times when that's actually a good idea, but it's kind of rare. So for this class, I would say just try to always keep your class widths to be equal size here. So that's the idea of separating the data in classes. Now, once you've done that, once you've broken them up, then we can draw frequencies based on these classes. So we could say, here's my class from 0 to 2, from 2 to 4, from 4 to 6, from 6 to 8, and 8 to 10. And why don't I just do a little frequency distribution here? So how many are between 0 and 2? Going across here, 1 that's between 0 and 2, 2, 3, 4, 5. Looks like there are 5 that are between 0 and 2. Now between 2 and 4, 1, 2, 3, 4. 4 of them there. And then 4 to 6, 1, 2, 3, 4. 4 of those there. 6 to 8, we've got 1, 2, 3, it looks like. And then lastly, we have 8 to 10, that's 1, 2, 3, 4, and it looks like that's all. So that would be a frequency distribution based on the classes that we've created here. Now, of course, someone else could decide they wanted classes that were a width of 2.5, and then we'd have 4 classes, and then their frequency distribution would look different. And that's okay. Again, this class, a lot of times, there's not one correct answer. Someone could have done 10 classes, 0 to 1, 1 to 2, 2 to 3, and so on, and then their distribution would also look different. So it really just depends on the context, which way you might think would be better to present the data. Unfortunately, something we'll see later is that sometimes people will choose the classes in a way to make the data skewed to justify whatever position they're trying to claim. So yes, we have this freedom in how to choose our classes for a given example, but some people misuse that privilege and do it to try to skew the results to, show off whatever it is they want to show off. So it is best to try to be as impartial as possible when you're doing these things, but it's not always going to be happening out in the real world. What if we wanted to make a bar graph out of these? Well, we basically can, except we're not going to call it a bar graph. We're going to call it a histogram. So it's going to look basically the same here. The only difference is when we draw this here, so it starts out with 5, and then 4, and then 4, and then 3, and then 4. If you notice the difference between this and the bar graphs saw before, the bar graphs, the bars were actually, like, there was a space between them. They were not connected to each other, whereas in a histogram they are, and that's because these are quantitative data, so of at least an ordinal level of measurement. So this 2 right here, it's grouping up. It's right in between the 2 classes there, so the classes are really touching each other. Whereas when we talked about, states that they were born in, California, Arizona, Nevada, New York, those are completely separate things. There's no way to put them in a right order. There's no way connections directly between them. I mean, yeah, physically maybe there's borders, but these, when we have numbers here, it's a more natural thing to have them right next to each other because the numbers are right next to each other. So for histograms, we connect the boxes. For bar graphs, we don't. With that said, it's not that big of a deal in my personal opinion, so I'm not going to worry too much about it. The last thing to talk about for this video are these things called stem and leaf plots. And I may be giving myself away that I'm a bad teacher or something here, but I've never really seen anyone in the real world, quote unquote, actually use stem and leaf plots. It's just not something I've ever encountered. And to try to do it for this data below here might be a bit too much. So let me make a new data set here. Let's say I did 4.2, 3.8, 2.9, 3.5, 2.8, 4.1, 4.0. Maybe one more, 3.2. So let's say it's a new data set here. What you do is you're going to break off whatever the last digit is. Those are going to be the leaves. And whatever everything before that is, that's your stems. So in this case, I made it easy with just 2 digits. So when you break off the last one, we have this. So everything on the right of these lines, that are the leaves. Everything on the left are the stems. So you go ahead and you write the different possible stems on the left. The only stems I have here are 2, 3, and 4. And then the leaves are going to be all the different leaves that have the same stem, and you put them in increasing order. So if I look at, for example, the stem of 2, I have a 2.9, a 2.8, and that's it. So I have the 8 and the 9. So that represents having one data that's 2.8 and another data is 2.9. For 3, I have a 3.2, a 3.5, and a 3.8. Cross those off there. And then for a 4, I have 4.0, 4.1, 4.2, and we have that. So this becomes a stem and leaf plot. And if you imagine looking on the side here, it's really giving the same kind of information that a bar graph would, in that the further out you go, the greater frequency is people in that range. The advantage of this is when you look at it, you can actually go back and give me the exact data that you had. Whereas if you have a histogram like this, all I know is there are this many people between 8 and 10. I don't know the exact numbers between 8 and 10 they were. They could have all been 8.1. They could have all been 9.9. I don't know, just something between 8 and 10. Whereas a stem and leaf plot, I can know there was exactly one data that was 2.8. So the stem and leaf plot does let you go back to the original data if you so choose. But otherwise, there's not much need to do it in that fashion. And like I said, I've never encountered it in the wild, so to speak, but maybe I just haven't experienced it myself. I would be very interested if any of you have ever seen a stem and leaf plot in another class and actually used it. Feel free to let me know about that. But for us, it's just another example of a way to organize data that is quantitative.